begin the class, and probably this is the last class of molecular spectroscopy. So I try to uh, finish off this molecular spectroscopy today by dealing Raman spectroscopy. So before Raman spectroscopy, let me uh, give you the just recap of what we have seen so far. Uh, First, as I said, molecule has a freedom, and that is actually exploited, or that can be molecule when it is irradiated with the electromagnetic radiation. uh, Based on based on the type of electromagnetic radiation, uh, when it is irradiated on the molecule experience some effect. That effect is actually studied. So that is what actually spectroscopy is all about. So it is about interaction of matter. Matter here it's molecule. So in spectroscopy in general, it is useful for structural elucidation, and so different molecular parameters can be determined. So some of the idea about the molecule. So it's a qualitative aspect. The qualitative aspect of the molecule can be determined. So, as I said, spectroscopy is actually it is based on the quantization of energy levels. So, molecule has different energy. Molecule has different energy. The total energy of the molecule is, according to Born-Oppenheimer approximation, it's a sum of different energies: translational, rotational, vibrational, electronic, chemical, and nuclear. So it's a sum of all this energy is nothing but the total energy of the molecule. And translation energy, since the energy levels of translation energy is not quantized, so we don't have translational spectroscopy as of now. As of now, I underline that word, or I put it in an inverted comma. In future, it may be uh, definitely there may be quantization that is not visible as of now. Probably times to years to come, that can also be studied. Some useful information uh, can be extracted out of translation spectroscopy, right? So rotational spectroscopy, as I said, the condition is molecule must have a permanent dipole moment. Only those molecules with the permanent dipole moment can be studied uh, are studied in rotational spectroscopy. And the and it should be in the gaseous state. Like a molecule must be in the gaseous state so that it will have that freedom, rotational freedom, and that energy level separation. All this we have said, and the important parameter or important aspect of the molecule studied under rotational spectroscopy is internuclear distance, and that can be extended to different other things. And next spectroscopy, which we studied, is vibrational spectroscopy. The uh, molecule will have this property called vibration even at 0 Kelvin. Uh, the vibration energy level of the molecule, when it is the energy gap, the vibration energy gap in the molecule is which is equivalent to the energy of IR radiation. So that is why the IR radiation is used for studying vibration spectroscopy. And vibration spectroscopy, the condition is molecule must have permanent dipole moment, or at least during vibration it should produce dipole moment. So only such molecule will give you the IR signals. And study of vibration spectroscopy in organic chemistry. We try. It is useful to study the functional group, and it is uh, one of the widely used spectroscopy in chemistry, because most of our application comes from organic chemistry. It is like that. Chemist is so close to the IR spectroscopy. And in IR spectroscopy, we have seen what is fundamental band, what is hard band, what is overtones, and how the molecule is assumed as per the quantum mechanics. Quantum mechanics assumes the simplest the molecule, which is the diatomic molecule, And when it comes to diatomic molecule, it is a heteronuclear diatomic molecule, which will give you the IR signal, and the diatomic molecule is approximated as a simple harmonic oscillator. That is, vibration is actually considered as a harmonical, something like a pendulum in the physics you studied in your school days, or in your ancillary physics, where you studied the pendulum, the moving pendulum or swinging pendulum will obey the classical Hooke's law, from which the potential energy of the Hooke's law can be, the classical law, the same energy, the same thing can be the same the oscillating pendulum like thing can be applied to the molecule. So you get an energy expression for the simple harmonical oscillator. So simple diatomic molecule is, it is otherwise called a simple harmonic oscillator, and we have seen the corrections in the energy expression. That is, the assuming the diatomic molecule as a simple harmonical oscillator is not always true, because at higher vibration energy level, that assumption is not correct. So hence we actually approximated the even the diatomic molecule at higher vibration state as anharmonic oscillator, and we have seen in the last class the equations and the corrections, and thereby we compared the energy expression of the energy expression as well as the potential energy diagram of simple harmonic oscillator and unharmonic oscillator. A molecule is assumed as how a molecule is assumed as a simple harmonic oscillator, when it is assumed as an unharmonic oscillator. What is the difference? All those things we studied, and we have seen what we call as dissociation energy calculations and all these things. So in this class, we will see some other concepts in both rotational and vibrational spectroscopy in terms of polyatomic molecule for a while, and we move to what we call as Raman spectroscopy. So this is the next one. Maybe I leave you by 12:40. Uh, so at the maximum 12:40. So at least nearly one and a half hours, or more than 1:15, right? So it is almost some 60 to 70 minutes of class I'll try to cover, right? So I leave by 12:40. I don't extend too much. At least 12:40, right? Okay. So this is as I said earlier in the one of the few concepts which I just want to add in the rotational spectrum as well as the vibrational spectrum, which is your polyatomic molecule as a thing, and we'll do one or two problems and we'll move to Raman spectroscopy. In Raman spectroscopy, I'm not going to deal too much theory into, at least the formation of the Stokes, anti-Stokes, and pure rotational Raman, vibrational Raman spectroscopy, a basic idea. So those things we will discuss, and laser Raman spectroscopy. So which is that also we'll discuss. Okay, so we done a few problems in the last class with reference to the vibrational spectrum. So now I shall just I'll tell you, these are the things which I have told you. I'll just show you, and okay, so these are the things as I said. Okay, so we have seen the rotational spectroscopy, the things rotational spectroscopy, and energy of rotational rigid rotator, the simplest diatomic molecule, uh, which is which I call this as a rigid rotator. as per the quantum mechanical approximation, whose energy is given by this expression, which is B r h square 8 pi square I j into j plus 1, where j can have value 0 comma 1, right? And in terms of wave number, the energy expression can be given as b bar into j into j plus 1, where b bar is nothing but h by 8 pi square I into c. So these are the things, just a recap of what we have seen. So if you take the energy levels of the rigid rotator, the lowermost energy will be 0. This is 0. The second E1, the first J, when J is equal to 1, which is nothing but J is equal to 1, J is equal to 0. So this can have, substitute this value. This is so 2B bar. So other value would be 6B bar. So this is J is equal to 2 and J is equal to, this is 12B bar, J is equal to 3, and this is 20B bar, J is equal to 4, and this is 30B bar, where J is equal to 5, this is J is equal to 6, which is 42 bar. Though the energy levels they are not equally spaced, they are dissimilar, but the corresponding transition, I just told, this will give you a line which is nothing but 2B. And some molecules, if this molecule undergoes this transition, the line formed by this will be, maybe I'll write here 2B, this is 4B. And molecules, rotating molecule which is having this energy will undergo by absorption of microwave. They will result in what we call as a line called, which is 6B. And another one is, subsequent lines are, so 8B, etc. So the energy levels are not symmetric, but lines formed by the different transitions are 2B, 4B. There is some harmony, right? There is some symmetry in it. And the distance between the two, the spacing, which is nothing but 2B. So 2B is the consecutive line, the spacing between the any two rotational, any two consecutive rotational, I put it like any two consecutive rotational lines is equal to 2B. So this is what we have seen. So 2B is equal to, so which is nothing but 2 into a h square, sorry, h by 8 pi square I c. So what is then B? B is equal to, that is half of it. So by knowing that this, I can find out B value from this. B is equal to, by knowing B, I can find out I value. From I will be, the unit will be kilogram meters. We have done many problems. From I value, I can get I is equal to mu r square. So from this, I can calculate what you call as well internuclear. So this is what normally we do. So this approximation. So when J is equal to, at lower energy level, this is what is your different energy levels. Right? J is equal to 0, J is equal to 1, J is equal to 2, J is equal to 3, J is equal to 4. No problem. But higher rotating molecule, uh, when they are at higher rotation energy level, the internuclear distance, what is rigid rotator? Rigid rotator is nothing but this internuclear distance, this bond distance. Bond distance is always a constant. So for a molecule, Rigid rotator means the rotating molecule, the internuclear distance of the rotating molecule will never change. That is what is the meaning of rigid rotator. It is rigid in the molecule, internuclear distance is constant. But that cannot be true. So this can be true. So the always a constant. This can be true only at low J values for any molecule for the matter. But at higher J values, so the what do you call as the fixed internuclear distance or constant bond distance or bond length uh, at higher constant bond length concept is not valid. It's not valid as a thing. So that is at higher J values. Sorry, higher J values. Your bond distance changes, bond length changes. So therefore, rigid rotator or the molecule cannot be approximated as rigid rotator at higher J values. So then they are called as non-rigid rotator. Therefore, non-rigid rotator is the idea. So for any molecule, when it is at a higher J value, you cannot say it as a rigid rotator. It's a non-rigid rotator. So therefore, your entire equation changes. So this is what is the assumptions. This is so approximation. This is what is the new way of looking at the molecule. So EJ, so which is equal to J into J plus 1, which is your what do you call as well? The B J into J plus 1, right? And you just add a what do you call as J square into J plus 1 square. This is what is the new energy level equation. This is a non-rigid rotator application. So therefore, the energy expression is this is in terms of wave number. Energy in terms of wave number. Where D is nothing but like where B bar. You know what is B bar for any molecule? This is called as this is a rotational quantum number. It is a rotational constant, which is a characteristic property of a molecule. So for a molecule, it's a characteristic property of a molecule. So every molecule will have, any rotating molecule will be associated with this a constant called rotational constant. It's a characteristic property of a molecule, like a boiling point, melting point. So for a molecule, it's a fixed value. And D is called as a new constant, which is called as centrifugal distortion constant. It's called as centrifugal distortion constant. Centrifugal distortion, which is called as a centrifugal distortion. Right. So what is it? Is there any relationship between things? So that means when you compare the energy levels, maybe this is like a rigid rotator assumption. Molecule is assumed as a rigid rotator. But when the same molecule is assumed as a non-rigid rotator, that is my way of looking at the molecule. Now it is non-rigid rotator. That means at higher vibration, at higher rotation level, the molecular rotation energy of the molecule actually, you cannot assume that is the internuclear distance changes. So this assumption at lower molecule, this assumption not much difference in J1 and J0 or for that matter J2 etc. Not big changes, but a higher vibration energy level when J is equal to 5, 6 etc. So there is a big difference, uh, which is J is equal to 5. So J is equal to 5 of I might assumption as a molecule as a non-rigid rotator and assuming it as a rigid rotator. So the at higher vibration energy level, there is a big difference. In other words, the non-rigid rotator rotation energy level is always lesser than the rigid rotator energy level. So at higher energy level, at a higher rotation energy level, the gap between the rigid rotator and the rigid rotator widens. But at the lower rotation energy levels, there is not much difference, right? So the selection rule, my selection rule, not assuming the molecule as a non-rigid rotator, so the same selection rule, there is not much change. So therefore, uh, the uh, the energy levels obtained. If this is my rigid rotator, giving the line 2B, 4B, I told you what is that the lines. But this is the same thing when I assume at a non-rigid rotator, I show it in a dotted line. So I get my energy level. So this is my increasing in energy. So this energy gap is once again between the non-rigid rotator, which give it in a dotted line, and rigid rotator, I give it in a dark line. So which is also 2. So the difference is not the matter. Only thing is the energy levels changes as then the placement of the rotation energy changes, but the consecutive energy level difference is almost 2B, so that is not a problem, right? So the only thing is a molecule, rotating molecule is the best approximation. The best approximation rotating molecule is a non-rigid rotator. Assuming as a non-rigid rotator is a better approximation when compared to the rigid rotator approximation, because the rigid rotator in rigid rotator approximation it is only correct when the molecule is when the molecule is rotating in the lower rotation energy level, that approximation is okay. But when the molecule is rotating at higher vibration energy level, the rigid rotator approximation is not a correct approximation, because you cannot the bond distance should not be fixed constant, right? But likewise, so therefore, the best approximation is a non-rigid rotator approximation, which is otherwise called as real molecule. They are called as real molecule. Real molecule, how the molecule behaves, right? So that is what is the mean. So now coming to the distortion. Distortion I have written as D, centrifugal distortion, which is nothing but 4 cube divided by what you call as omega vibration, which is for my convention, I can write cube divided by the fundamental the vibrational frequency. Omega, some book they give as omega vibration, which is nothing but the vibrational frequency, right? So for so for a molecule, this is what is the thing. So this is nothing but a connection between the vibrational and rotational spectroscopy. So vibrational frequency is given by this omega, and by knowing the vibrational frequency, I can calculate the different other things also. I'll tell you. So therefore, vibrational frequency, the omega, when it is increases, vibrational frequency increases, the rotational constant, you know that rotational, not rotational constant, it's just a force constant, which increases, you know that. So vibrational frequency, or as I said, some book give as omega, which is 1 by 2 pi root k by, this is what is your. So when vibration frequency increases, your k value increases, and when k value increases, force constant, which is indirectly gives you the strength of the bond, the stronger bond, right? The strength of the bond, the strong bond, or stronger the bond, right? When k increases, strong the bond, When the vibrational frequency increases, this is also your D value. Centrifugal distortion decreases. Centrifugal distortion decreases. And normally, vibration frequency will be in the order of 10 to the power 3 centimeter inverse for a molecule, and correspondingly, my B value rotational constant for that molecule will be around 10 centimeter inverse. And the same, your D value, centrifugal distortion, will be very small in centimeter. So these are the connections. These are the relations between the frequency, vibrational frequency, rotational constant, distortion constant relationship for a normal molecule. So therefore, for small value of J, small value of J, J0, J1, J2, etc. So small value of J, the D bar, J square, J plus 1 square is almost negligible. Negligible. Right? So therefore, at lower value, this equation J is equal to B J into J plus 1 minus 4, this equation, not 4, the D, I mean D, I'll tell you the D bar, right? So this equation J square and J square, J plus 1 square, B bar. So for lower J values, this is negligible. This is very small. So therefore, at low value, non-rigid rotator molecule behaves as a rigid rotator. I'm just excluding this. Very small. Hence, it can be ignored. At lower J value. But when it comes to higher J values, so when J values is high, 110 and or more or above, this value, that is J square, J plus 1 square, is appreciable. It is becoming important, significant. They have become appreciably. It is an appreciable value, so it becomes important, and it becomes a positive. It becomes a positive, high positive value. It becomes appreciable because becomes high positive. The value becomes high positive. So it is in this equation, that is EJ, which is nothing but the J into J plus 1 minus D, this is what is it? The D, J square, J plus 1 square. So this part becomes very high or very positive value. So therefore, your energy value decreases. At a higher value, this becomes small. That is from this total, so you get it decreases at higher value. So that is why at lower value there's not much difference, but when it comes to higher value, it is all so close. They are compressed. They're becoming what you call as a bunch. They become at higher value. They become a bunch. A bunching of energy levels. They has become so close. Energy levels, bunching of energy levels. That is, they become. They become close. Right. So this is what is the expression, and we can give you the difference also, the delta E, in a faster way. I'll tell you that this is your rotation energy level, and so if you do that, it will be something like this. You can do it by your own, and I'll just give you the values, which is 4B J plus 1 whole cube. This is in centimeter inverse. So this is the difference in energy level, that is the delta E. The delta in rotation energy level with rigid rotator, it is slightly different, right? So this is the energy level, you can get it out. And suppose for HF, for example, we do the problem for HF, the pure rotational spectrum uh, for HF in pure rotational spectrum, rotational spectrum, uh, assuming it as the assuming it as assuming it assuming it as the assuming it as non-rigid rotator, non-rigid rotator, right? So the equations, the spectral line equations, which we see. Uh, okay, so this is what is it? Assuming this as the rigid rotator. So this is what is it? The translational, the spectrum you get it, and say they give some value j plus 1. This is 41.122, and they show this is j1 minus 8.52 10 to the power minus 3 j into plus 1 cube. So this is what they said. This is what the wave number they give you. So you are asked to find out what is the B bar, D, and the vibrational frequency and force constant of HF. So they give this equation, which is showing that they are the rotation lines, the rotational lines they give. This is what is the rotational line, and this is the equation. From this equation, you are asked to deduce the following. You are asked to find out the following, right? So you get so this is about a rotational, non-rigid rotator, rotational rotating molecule which is obeying a equation. They may give you this equation, and you are asked to calculate a thing. So this equation resembles the delta E. This equation. This is resembles this equation. So therefore, so this is nothing but your 2b. So your 2b is equal to 41.122 centimeter inverse. So this equation resembles the energy difference equation, rotational energy difference equation, if the molecule is assumed as a rigid rotator. This is a general equation. And they are given this equation. Look at these two equations, this equation and this equation. Instead of 2b, they give some value 40.1. Like 4b, they give 4d, not 4b, it's 4d. 4d bar, which actually resembles 8.53. So from this, you can find out my b value is, which is nothing but 20.61 centimeter. Likewise, your d bar, which is 4d bar, which is 8.52 into 10 to the power minus 3 centimeter inverse. So from this, I can find out my d value, which is 2.13 into 10 to the power minus 3 centimeter inverse. Right? Centimeter inverse. Then from knowing d value, I know that this is another equation, that is 4b cube divided by the frequency square, omega square, vibrational frequency square. So now I know what is my B, what is my D. From this, I can calculate my vibrational frequency square, which is nothing but 4B cube divided by D. So which is nothing but 4 into the values, which is 20.51561. Look at these values. Centimeter minus 1 square cube divided by the d value, which is nothing but 2.13 10 to the power minus 3 centimeter. So from this, I can calculate my omega, and the omega, which is your vibrations frequency, as I said earlier, So which is nothing but 1 by 2 pi, 2 pi c if it is in the centimeter inverse, which is k by. So this can be you can find out from this value, which is, if you do this, this will be around 40 point centimeter. From this equation, I can find out my omega, and this is my answer. By knowing omega, I can find out my k value. K is nothing but the force constant, which is 4 pi square, and omega vibrational square, c square, then reduced mass. So reduced mass of HF. So this you can calculate. We have how I can calculate the reduced mass, which I told you in the previous classes. So by knowing this equation, I know what is omega, I know what is c. C is the velocity of light. From reduced mass of HCl, if I substitute everything, I can find out the k value, and k value is found to be, for this, it is 960 Newton per meter, which is very large. Which is very large. Which is a large value. Normally, it is around 450. For higher value, triple bond, maybe it can come to around 2000. So, but 960, which is quite large. So, which is very large, right? So that means HF bond strength of HF is high. It is high, right? So, which is a strong acid from HF to HI. So HI is the strong acid. This is a weak acid, because the bond energy between the two is which is very high. So weak acid. HF is a weak acid. And whereas HF, if you the K value with reference to HF and HI will K value will be very less. So the vibration will be, if you this is how, if this is your vibration, this is your bond length. It's a very tough thing. That is 9,006 centimeter inverse. So you cannot extend, you cannot pull the string, you cannot pull the spring. It's very difficult to pull the spring. The spring is so tough, because the bond energy is so tough. Bond is so strong. But when you bond is very weak, you can elongate. Maybe this is my HI for the matter. So this is your HI. HI will be something like this. This is for HF. Probably this is for your HI. That means the bond displacement. Look at the displacement. This can be elongated. So the spring can be elongated. So your K value is small. K value is small. K value is small. So this is the connection between the rotational constant and all this thing. So I can find out my delta E is equal to, this is my equations I have to remember. Delta Ej, which is equal to J plus 1, which is equal to 2B bar minus 4D bar into J plus 1 square, which is in the centimeter. These two equations, this is first equation, and this is another equations. This is your second. This is these two general equations. That is the difference between the rotation lines. In assuming the molecule as a rigid rotator, I can find out many things. I can find out from this I can find out the rotational constant of the rotating molecule, and the centrifugal distortion. By knowing centrifugal distortion, I can find out the vibrational lines, vibrational frequency of the molecule, from rotational spectrum. I can find out the vibrational frequency of the molecule. From vibrational frequency, I can say the rotation force constant. From rotation or the force constant, I can say the bond strength of the molecule. So this is a connection between the from rotational spectrum to vibrational spectrum. Okay, so polyatomic molecules, I'm not going to once again deal too much. At least a few things about the polyatomic molecules. So this is a polyatomic molecule. It can be a linear molecule. Linear molecule is one assumption. Polyatomic molecule. This molecule is classified based on moment of inertia. Uh, Moment of inertia, right? So based on the three axes. So for this one, the linear molecule, which is like where uh, Ia is equal to 0. So on one side, the molecular axis side, the moment of inertia is 0. But other two sides which are perpendicular to the molecular axis, like your x, y, z direction. So these two are IC, they are equal. So you therefore you will have only one moment of inertia, one moment of inertia, one moment of inertia for this molecule. So one moment of inertia, this molecule obeys delta J is equal to plus or minus 1. This is a selection rule. And generally, your diatomic molecule is an example of uh, this type of molecules. And even the linear molecules like carbon dioxide, which does not have permanent dipole moment, so microwave inactive, and acetylene for the matter, acetylene, which is where a triple bonded, I mean, C triple bond C. So all these are microwave inactive. They are microwave inactive. Okay, so inactive, but you have these molecules like right. So these molecules, all these molecules will be microwave active, microwave linear molecules, but they are hetero in character. So this is one type of molecule. So they will all this will have only for this molecule you'll have only one B value. So one moment of inertia, one B. You'll have only one B. Right. So some molecules they are called as spherical top molecules based on the moment of inertia. They are spherical tops. So this molecule, based on the classification based on moment of inertia, they are on all the three direction x, y, z. That is what is I give it as xa, xb, xc. But all the three axes, so they are same. So these molecules will also have what you call as where one moment of inertia, and therefore it will have one p value. But in general, most of these molecules, most of the spherical top molecules, they have the permanent dipole moment is 0. So hence they are microwave inactive. Microwave inactive. So if you generally in the point group now, if the molecule classification based on point group, these molecule, the special case molecule like the tetrahedral molecule, the octahedral molecule, and the icosahedral molecule. So these molecules are generally belonging to the spherical top molecule, and if they are not, if they have permanent dipole moment and having this type of moment of inertia, they behave as a linear molecule. It's a normal diatomic molecule, but most of this molecule they have a symmetrical character, a symmetric in terms of moment of inertia. So most of them are microwave inactive. And if at all they are active, they will be having one B value. They will have one B value, like a normal diatomic molecule, right? Then the other thing is, of course, all this involves many derivations or thing. I'm not going to give you. I'll give you the nutshell because you can have the problems here also. And the other classification is symmetric top, the molecule which are called a symmetric top. Here you have two types of molecules. One is called as your like prolate symmetry. Yes, prolate symmetry, symmetric top, where your Ia is less than or equal to, these two are equal. IB and IC are same, they are equal, but your Ia is less. Unique moment of inertia. Ia is your unique, that one. And generally, and here, these molecules, for that matter, which are the first case linear molecule. So these molecules which are inactive, they are generally the d infinity H point group, and the others are maybe the C infinity V point group molecules are linear molecules which are active, microwave active, and these molecules are microwave inactive in terms of point group. And this is your symmetric, the TD point groups, the special case molecules, they are microwave inactive. But even if molecules are A, B, A, C, they are equal, and if have permanent dipole moment, they behave as a simple diatomic molecule because they will have only one I value. The Proudite symmetry, so here you can have different, they have different B values. So the B value, you have three set of B values, three set of B values. The values, you have three set of B values. Out of three, two will be the same. So therefore, in simple, two I values, two I values, and two B values. This is what is it. So you will have two B values. So in technically it have three set of B values, but two values are same. Two values are same. So ultimately you will have two types of B values. So example, these Proudite symmetry, a C3V point groups, and the C3 point group generally they belong to your ammonia, then your CH3, CN, methyl cyanide. All those are examples of the Proudite symmetry. So then you have oblate symmetry, oblate symmetry molecule, symmetric top molecule. So as I said, symmetric tops. So this molecule likewise, this will have two I values, though they have three set of I values. Finally, that will be reduced to two I values. I mean, and the three set of I values. I values will be IAB, which is equal to IB, which is less than or equal to IC. So this is your unique moment of inertia, which is less than the other two. So these two contribute for one B value, and this is for another B value. So therefore, two B values for two B values or two B values. Technically, A, B, C, three types of B values, out of which two will be equal. So therefore, this is reduced to two B values, two B's. Then finally, you will have the last thing, which is your asymmetric top molecule. Asymmetric top molecules where your IA is not equal to IB, which is not equal to IC. Like where you have three set of similarly rotational constants, A, B, C are three set of rotational constants. So you have three rotational constants for these molecules, right? So this is about the of course there will be different, it's all tough problems. You'll be given three set of rotational constant, and the spectrum is also a thing complicated. But when it comes to vibrational rotational spectroscopy, which we see in the last class, vibrational rotational spectroscopy, which in the spectroscopy, the selection rule is delta V is equal to plus or minus 1, whereas your delta J is equal to 0, comma, plus or minus 1. So this will form what you call as your PQR branches in the heteronuclear diatomic molecules, which we have seen in the last class, right? So the selection rule is something like where the selection rule is the vibrational rotational spectroscopy, where this is mu naught, then you have the plus mu naught uh, plus the uh, the selection rule, which we have seen the by selection rule, which is your delta V is equal to 1, delta J is equal to 1. This is your R branch, delta V is equal to 1, plus or minus 1 in the state, delta J is equal to minus 1. This will give you the P branch, delta V is equal to 1, delta J is equal to 0, which is your Q branch. Generally, these two are called as the parallel bands, and this is called as the perpendicular band. right? This is given by the nitric oxide. This is given by HCl. All this stuff, right? So let us not go into the too much of things at least. And for vibrational spectrum of the polyatomic molecule like carbon dioxide, acetylene, etc. Uh, the vibration line, the vibrational rotational lines, right? The PQR lines, the vibrational rotation line. That is the PQR branches, the PQR in PQR branch, the formation of PQR branches also formed here, and it will be absent for carbon dioxide. The alternative lines, the alternate lines is absent, which is absent in the carbon dioxide cases. The alternate PQR lines are in this absent. This shows these molecules are highly symmetric. They are molecules with what he called as the center of symmetry molecules, where the in the vibration rotational spectrum, that is PQR branches, in the PQR branches the alternate lines are absent. That shows the molecule is highly symmetric. They are molecule with center of symmetry. They are molecule with center of symmetry. But in the case of the molecules are the alternate lines are the alternate the molecule, once again these molecules are with the center of symmetry. The alternate lines are uh, what you call as less intense. They are called as less intense lines. The alternate lines are less intense. So therefore, that is the molecule with center of symmetry. Some cases it is absent. Some cases it is less intense, because your this is due to your I value half for your proton. For proton, that plays an crucial role. But in the case of carbon dioxide, where I value will be zero, uh, of course, technically your C3 will be C13 I value is half, but other the abundant C12 and C14, they are I value is equal to zero. Hence, alternate lines are absent. But here, that for your the acetylene, in the case of acetylene, the alternate PQR branches, in PQR branches, alternate lines are less intense. So the center of symmetry molecule can be identified from vibrational rotation spectrum. The alternate lines in the PQR branch of PQR branches, the alternate lines are either less intense or either it will be absent. So that shows that molecule is center of symmetry. The molecule is center of symmetry. For non-center of symmetry molecules, there is no difference. All the lines are intense. All the lines, there is no difference in the lines. But molecule with the polyatomic molecule, when they are having the center of symmetry, the molecule with center of symmetry, the alternate lines in the PQR branches, either they will be absent or less intense. They are less intense. The less intense, why they are less intense? There is interaction between the nuclear quantum number, which have definite I value, but in the case of carbon dioxide, the I value is zero. I value is zero because it is C12 and C14 dominates. Your C13 is I value is half, but C12 and C14 I value is equal to zero. So therefore, there the alternate lines are almost no alternate lines, but in the case of acetylene, you have this, right? So the number of rotation lines and number of vibration lines is given by the 3n minus 6 and the 3n minus 5 formula. This is for your linear molecule and this is for your non-linear molecule. So for the center of symmetry molecule, example, the carbon dioxide, the expected, you get 4 vibrational modes. So you get expected is 4 vibration lines or 4 fundamental bands, 4 bands. But a molecule with center of symmetry, this is expected. This is expected is 4 fundamental bands, but in reality, you get 2 fundamental bands. But for water molecule, your CO H2O, where n is equal to 3, so expected is 3. So 3 into 3, 9. So 9 minus 6, you get 3 expected vibrational bands for carbon dioxide. So you'll get 3 fundamental bands expected. In reality, you get 3. So This is also another way of looking at the molecule, whether the molecule is highly symmetric. So highly symmetric molecule with the molecule with center of symmetry, there is some difference. For carbon dioxide, the water molecule, so this is what is a water molecule. So your symmetric stretching, you get a band. For one band is for your symmetric stretching, and for your unsymmetric stretching also. Unsymmetric stretching, this is compressed and this is elongated, right? You get asymmetric stretching. This is your asymmetric. This is your symmetric, and you have the bending vibration. So you have the bending vibration. So you get. So these are the three fundamental bands. So three fundamental bands for water molecule. But for carbon dioxide, as I said earlier, the carbon dioxide, this symmetric stretching, still there is no dou mu by dou r, which is equal to 0. So no dipole moment created. So it is inactive. So IR inactive. So no band for this one. For our fundamental, the asymmetric stretching, and for asymmetric stretching, this is IR active. This is IR active. Why? Dou mu by dou r, which is not equal to 0. So therefore it is IR active. And as I said earlier, the C double bond C, this is one bending, and likewise the other bending will be this upward bending. So these two bending may be C3, which is equal to C4. So both will have the same frequency. So you will get, for which you get only one fundamental band. So this is what is there. By looking at the molecule, one can say whether the molecule is having center of symmetry character or not. So center of symmetry in point group or in the symmetry operation, this will have inversion symmetry operation. The molecule with center of symmetry will have this molecule with the center of symmetry. Those molecules will have inversion operation. The molecules will have inversion operation. Right, so that's it about your rotational and vibrational spectroscopy. A little bit about your Raman spectroscopy. Raman spectroscopy. I leave it by, as promised, I leave it by another 20 minutes, 25 minutes. Raman spectroscopy. So Raman spectroscopy is nothing but normally when I irradiate molecule with electromagnetic radiation, different phenomenon occurs. The phenomenon, நிகழ்வுன்னு சொல்ற மாதிரி different phenomenon occurs. What are the phenomenon? The molecule will absorb the radiation. They absorb the radiation. As a result, we have seen that absorption spectroscopy. They absorb the energy from the radiation. The absorption. Some will have reflection. Some will reflect the light. Reflect the light. They will reflect the light. Some will undergo what is called as refraction. Refraction. So not some. This is all happening. This is all happening at the same time. But so far we are only focused this particular aspect, this particular concept only. But there are other activities also happening. We just so far we neglected that. Refractive. They undergo refractive, and sometimes they some of the lights which are scattered also. They are scattered. Right? So when the light is irradiated over the molecule, different phenomenon occur. நிறைய நிகழ்வுகள் நம்ம சொல்றோம். இந்த நிகழ்வுகள்ல நம்ம இதுவரைக்கும் பார்த்தது அப்சார்ப்ஷன். அதாவது மாலிகுல் வந்து அந்த ஆற்றலை வந்து எடுத்துக்கொள்றதை பத்தி மட்டும்தான் இது வரைக்கும் நம்ம பேசணும். மற்றபடி நிறைய என்ன சொல்றது ரிஃப்ளெக்ட் வந்து அப்படியே வந்த வழியிலே போறது ரிஃப்ளெக்ஷன். தென் ரிஃப்ராக்ஷன் அப்படிங்கிறது ஒரு மீடியத்துல இருந்து இன்னொரு மீடியம் வரும்போது தண்ணியில இருந்து லைட் பாஸ் பண்ணும். தண்ணி பாஸ் பண்ணுறது the path of light is actually bent, right? It is actually bending. நம்ம காயின் போட்டோம் அப்படின்னா தண்ணிக்குள்ளார காயின் போட்டோம் பக்கத்துல தெரியுது. காரணம் என்னன்னா அது ரிஃப்ராக்ஷன் அப்படின்னு சொல்ற கான்செப்ட். ஸோ இதுவும் நடக்கும், ரிஃப்ராக்ஷன் நடக்கும். ஸ்கேட்டர்ட் ரேடியேஷன், ஸ்கேட்டர்ட் பொதுவாக பொருட்களை வந்து ஸ்கேட்டர் ஆகுது, தெரிக்கிறதுன்னு நம்ம சொல்றோம். ஒரு பொருள் எடுத்து ரொட்டேட் ஆகிற ஃபேன் மேல அடிச்சோம், ரொட்டேட் ஆகிற ஃபேன் மேல போட்டா என்ன ஆகுது, அடிச்சு அப்படி தெரிக்குது இல்ல. ஸோ தெரிக்கிறது, அது மாதிரி லைட்டு தெரிக்கிறது ஸ்கேட்டர்ட் ரேட், இதெல்லாம் நம்ம கணக்கில் எடுத்துக்கல, நம்ம ஒன்லி அப்சார்ப்ஷன் மட்டும் தான் எடுத்துக்கிட்டோம். ராமன் ஸ்பெக்ட்ராஸ்கோபி என்ன பண்ணுது, இந்த ஸ்கேட்டர்ட் ரேடியேஷனை கணக்கில் எடுத்து ராமன் ஸ்பெக்ட்ராஸ்கோபி வந்து கணக்கில். ஸோ இப்போ மாலிகுல் இருக்கு அப்படின்னா, திஸ் இஸ் மை மேட்டர் மாலிகுல். ஸோ இஃப் ஐ இன்டர் ஃபோட்டான்ஸ் அப்படிங்கிறது ஒரு மோனோக்ரோமேட்டிக் ரேடியேஷன். I consider monochromatic radiation. Monochromatic radiation, a particular only one wavelength, one lambda, the monochromatic. So when I irradiate the photons, which is having all photons having same wavelength, right? So what happens? I said different phenomena is occurring, but I don't bother about absorption. I don't bother about the reflection, refraction, all those stuff. I only interested in the what you call a scattered radiation. Ethana scattered radiation in a concept of consider. So this is my scattered. Scattered is we don't know where it is. It is scattered is always scattered. It is not unidirectional. It is disoriented, right? The scattered radiation or scattered radiation. So scattered radiation, once again, if I call this as a radiation as photon, the scattered photons. The photons are scattered photons. So initially, the photon will have incident radiation. This is my incident. Incident is what I irradiate. Incident radiation. Incident. Right? So this is my scattered radiation. So two things I am considering. So scattered photons. This is, if I call this is my photon. This is another photon. So two set of photons is my interest in Raman. So this is my photon at the incident, photon at the scattered. So two things I have to consider in Raman spectroscopy, and I could see that in Raman spectroscopy we have three set of photons, scattered photons. You have three set of scattered photons. Three set of scattered photons. Scattered. Three set of scattered photons. One, what is the first photon? The first photon is same. The scattered photon energy, there is no change in the incident photon energy. What you incident, that light is scattered. That light is scattered. The same, there is no change in any energy. The energy is conserved. The scattered energy, the scattered photon energy and the incident photon energy is almost same. And it is like your elastic scattering. Elastic scattering. And it is called as, the other way it is called as Rayleigh scattering. Rayleigh scattering, which is a elastic scattering. And in some case, some scattered lines, which is the incident line, which is less than the scattered line. Our scattered line, actually, there is some energy increase in scattered line. And this scattered line, and another scattered line where the incident light energy is greater than the scattered. Our scattered line loses some energy. So these are the two types of scattered radiation, and they are called as inelastic scattered radiation. Inelastic scattered radiation. Scattered radiation. And they are called as Raman scattering. They are called as Raman scattering. And this scattering, where there is an increase in energy in the scattered radiation, they are called as, they form what you call as anti-Stokes line. They are form anti-Stokes line. And the scattered line, which actually loses the energy, the lesser energy than incident radiation, they call as Stokes. They form Stokes line. So forming Stokes and anti-Stokes lines are called, it's because of Raman scattering. And remember, if I have 1 lakh or 1 million scattered lines, if I have 1 million scattered lines, that means I have to assume that if I incident 1 million incident lines, incident radiation, I will have 1 million 10 to the power 6 scattered lines. you'll have 1 million, almost one. Assume that if I have 1 million incident line, I have 1 million scattered lines, because I'm approximating other things are zero, absorption, refraction, other I'm not considering at all, right? So this 1 million, out of 1 million scattered radiation, almost 1 million will be Rayleigh scattering. So in the 1 million scattering, some 6 scattered lines will be Raman scattering. So look at the difference. So 1 million incident radiation, I expect 1 million scattered radiation. Assume that in 1 million scattered radiation, almost 1 million will be Rayleigh scattering. Out of 1 million, some 6 or 7, some very minimum will be a Raman scattering. So detecting this requires a sensitive photograph, a camera. So that is the important aspect of the Raman spectroscopy. Detecting this Raman study of the inelastic Raman scattering is nothing but Raman spectroscopy. Study of Stokes and anti-Stokes lines are called as Raman scattering. And in the technical Raman scattering, all type of molecules, be it solid, all type of molecule can be recorded. All type of molecules can be recorded. That is crystalline, amorphous, the solids, you can do that crystalline, amorphous, and the gas, liquid, you have coordination complex. So here, so anything can be recorded in Raman spectroscopy. There is no bar in it. It can be taken as a fingerprint of a molecule. Anything can be recorded. And usually we use visible radiation for a source of light. So visible radiation, right? So initial Raman used mercury arc lamp. The first generation the mercury arc lamp is actually used. Blue radiation was used, but nowadays Raman spectroscopy is the laser is integral part of Raman spectroscopy. Laser Raman spectroscopy, because the laser is a source of Raman. The requirement of any source of Raman, normally the light which we use, monochromatic radiation, that is, the lasers are monochromatic in nature. And the other properties of the requirement of the incident radiation is actually fulfilled by lasers. So laser being visible radiation, light is visible radiation. So the laser Raman spectroscopy is used. And coming to the condition for molecule to be Raman, it is your vibrational. Raman spectroscopy is actually the vibrational part of the molecule is actually the study. So it's Raman spectroscopy is actually indirectly, it is a vibrational spectroscopy. Right? So the condition is the molecule must have permanent it must have a permanent polarizability, or the molecule must during change. Of course, you cannot have permanent polarizability. Permanent polarizability is nothing but it is formed during induced dipole moment. Even a molecule which does not have dipole moment, they can produce dipole moment at a different electric field. That is called as your induced dipole moment. So mu induced dipole moment. You are making the molecule a charge separation. A permanent dipole moment is permanent charge separation. Induced dipole moment is when you keep the molecule on a different electric field, which is it will produce a dipole moment. So that is equated with a constant, and this is called as polarizability. A concept called polarizability. So dou alpha by dou r must not be zero. That is when the molecule in other words, normally in Raman spectroscopy, the ellipsoid of polarization should not be spherical. That is what is the condition. Ellipsoid of polarization, right? So ellipsoid of polarization should not be spherical. So if it is spherical, it is Raman inactive. Spherical, if it is Raman inactive, right? So in general, this is what is happening. I just show it in energy diagram. So if you take, this is your electronic energy. This is your E ground state. This is E excited state. And you know the different vibration level I can put. This is V0, this is V1, this is V2, this is V3. It goes V4 up to this. I can have some 10 vibration energy level. So most of the molecule will be having the ground electronic state and zeroth vibrational state. Suppose if I irradiate my photons, right? I'll show it in a different color. So if I incident, this is my incident radiation, and the molecule is excited. The molecule is excited. It moves to higher state, some state which is called as a virtual state. Virtual state is a higher vibrational state, higher vibration energy state. It goes to some virtual state and returns to the same vibrational state, returns to the same vibrational state. This is called as Rayleigh scattering. This is called as Rayleigh scattering. So if I draw the diagram in energy in the energy order, this is my most of this is my V is equal to 0. This is my Rayleigh scattering, right? And if the molecule goes to some virtual state, the molecule goes to virtual state or scattering, which scatters to higher virtual state and returns to some higher vibration state. So here the difference, the molecule actually loses energy. The scattered radiation, the incident radiation, the scattered radiation. This is my scattered radiation. This is my scattered radiation. The frequency of scattered radiation is less than the incident radiation. The difference is this is my losing energy. So where the energy is lost, the photon losing the energy to the molecule. So this is my Stokes line. This is my Stokes line. The energy of the Stokes line is less than the incident radiation, which is my Stokes line. Supposingly, I do it in a different line. This is my, maybe I give it this by this line or a green line. Right? Not green line because your molecule, I show it in the green line, maybe a yellow line. Right? I start if the molecule incident in the molecule which is having higher vibration energy absorbs the photon and goes to virtual state and scatters and returns to say lower vibration state. Here the photon initially starts at the the photon here it is absorbing. The photon here it is absorbing, but it is gaining the energy. There is a difference in energy. So here it is gains. So the photon actually takes up energy from the molecule. This is your scattered radiation. This is my incident radiation. So this is my mu s scattered radiation. So in this case, so it is like something like this. Something like this. Maybe I'll put it like so this is my scattered radiation. This is my another scattered radiation. This is my scattered radiation. This is my scattered radiation. So this is called as Stokes line, and this is called as anti-Stokes line. Look at that energy where this the Stokes line is at a higher energy level. Anti-Stokes line is at a higher energy level. Stokes line is at lower energy level. And the line height is, look at the height. This is your intensity. The intensity, which is more intense, Stokes is more intense. This is less intense. Why? Because it starts from lower vibration energy. Stokes starts from lower vibration energy, which are highly populated, but anti-Stokes starts from higher vibration energy, which are less populated. So intensity is directly proportional to the population. So therefore, Stokes lines are high. Generally, the what you call as well. The more written. So what we studied is called as vibrational Raman spectroscopy. This is called as vibrational Raman spectroscopy. That is the vibration energy of the molecule actually changes. The scattered line, the vibrational energy difference changes. For Stokes, the vibration energy actually, the scattered radiation will be lesser, which will be lesser energy than the incident radiation. Whereas your the anti-Stokes line, there is an increase in vibrational, the frequency, the scattered vibrational energy is actually increases. How it increases? It takes up the energy from the molecule, right? So this is what is your thing. And the last one is called as rotational Raman. I'll deal with the pure rotational Raman. Then we'll stop here. Pure rotational Raman. So pure rotational Raman spectroscopy, right? So Raman, PRRS, right? So what does it mean? So once again, the two rotational lines, I mean two electronic, this is your ground state, this is your excited state. And most of the molecule, you know that. So this is your V0, this is your V0 state. Sorry, please, I'll correct it. I'll leave you by another 5 minutes. Don't worry. So this is V0 state. This is V0 state. This is V1 state. And as I said, this is V2 state, etc. And this will have the rotation lines also, right? This will have rotation lines. This is J0. This is J1. This is J2. This is J3, etc. I'm only focusing. Most of the molecule will have zero vibration, I mean zero V0 state. But when it comes to rotation level, J0 is not, that alone is not highly populated. That distribution can be varied. Suppose if the molecule from this state, J0 state, right? J0 state goes to, this is my virtual state. This is my virtual state. Go to higher vibration state, and this is returning to the same state. That is from J0, it is scattered radiation, that is also J0. Look at that. So V is equal to 0. This is V is equal to 0, right? This is my scattered radiation. This is my incident radiation. So this is your Rayleigh scattering. This is your Rayleigh scattering, right? If some molecules, say I'll take this one, starts from J0, go to virtual state, and they loses the scattered radiation stops here. So this is my scattered radiation, this is my incident radiation. So what is this? This belongs to V0 and J0, and here it is V0 and J is equal to 2. J is equal to 2. So the delta J is equal to plus or minus 2. This is a selection rule. That is, the molecule is, the scattered radiation is the frequency of scattered radiation, the energy of scattered radiation, which is less than the energy of incident radiation in what terms? In the J0 terms. J is equal to plus, right? So they are J. This is your rotation energy terms. There is no change in vibration energy. So therefore, this will form a Stokes line, something like this. So this is your Stokes. Because Stokes is always lesser than the incident energy. Supposingly, if J is equal to 2 molecule, absorb the energy, go to virtual state, and returning to the vibrations, I mean J is equal to 0 state. So this is my incident radiation, this is my scattered radiation. So here V is equal to 0. For both the thing, it is V is equal to 0. But J is equal to 2, I mean J is equal to 0 for scattered radiation. This is J is equal to 2. Look at that. There is an increase in energy. There is an increase in energy of the scattered radiation by how much? By plus 2. Some of the energy from rotation of the molecule is taken. So therefore, this is my anti-Stokes. This is my anti-Stokes. So anti-Stokes line of pure rotation Raman and Stokes line of pure rotation Raman, our intensity is almost same because we are dealing with the rotation energy level. We are dealing with rotation energy level, rotational energy level. We know that all the rotational level energy levels are equally populated. Not exact. Some of the higher rotational energy level may be populated. That's a problem also, right? So this is how the rotation energy level. And remember, the selection rule is delta zero. Pure rotation Raman 0 plus or minus 2. This is your delta J, the selection rule for the Stokes and anti-Stokes. And this is a general rule. The J is equal to J is equal to the B J double dash minus J dash when J double dash plus J dash uh, plus 1, right? So this is your so substitute that. This is your the rotation lines. This is your rotation lines, rotational lines, and rotational lines in your rotational lines in the Raman spectroscopy. And the first one is the rotation lines. This is your Rayleigh scattering, and this is your the Stokes line will be here. I mean, this is your anti-Stokes line, and this is your Stokes line. So this is your Stokes, and this is your anti-Stokes. The first line will be 6B, and subsequent lines will be 4B. The subsequent lines will be 4B. And this is likewise. The first line will be 6B, the subsequent lines will be 4B in the Stokes and anti-Stokes. So from this, you can find out even for homonuclear diatomic molecules, this is pure rotation Raman is active. You get pure rotation Raman. So the pure rotation spectrum, homonuclear diatomic is inactive, whereas homonuclear diatomic molecules are pure rotational Raman active. So you can calculate internuclear distance from pure rotation Raman, right? So I'll stop here. Maybe if time permits, in the next coming classes, I'll deal with some of the problems in Raman spectroscopy, where the interesting thing is you can calculate the internuclear distance of the homonuclear diatomic. Generally, the problems will be vibrational rotational Raman and the what do you call this the rotational pure rotational Raman spectroscopy. Only in these two things you get problem. The calculation of internuclear distance, right? We'll see the next class. Right, thank you.
Thanks. Thanks.